Welcome, everybody. I hope you are having a good day today and will enjoy our webinar. Today, I'm going to be talking about NASA's healing and strengthening of commercial silicon carbide toes using microwave irradiation. Next slide, please. So, to give you a little background and motivation on how we came up with this project was I was working on silicon carbide fibers for ceramic matrix composites. And in this case, the matrix is also silicon carbide. These kind of materials have applications in turbine blades, heat exchangers, and they're really often used in areas where high temperature is required, structural stability, and long hours of operation. For example, the hot section components of military and commercial gas turbine engines. Next slide. So some of the benefits of this is that the CMCs offer high structural reliability and temperature capability. Compared to other metallic components, there is a reduction in engine weight, cooling air requirements, fuel burn, harmful exhaust emissions, as well as improved thrust to weight ratios. And the goal of my particular project at the time was to develop a ultra high temperature silicon carbide fiber toes that are commercially available. Okay, thank you. Next slide. So when I first started working on this project, my job was to convert these commercial fibers. And the very first thing I did was work on these fibers using an electric furnace. And electric furnaces, in this case, is a tube furnace, but other regular furnaces are used to do batch work a lot of times. Not when they're initially converted, the fibers are initially converted to silicon carbide, but for other processing steps. So in this case, I just wanted to look at to see if there's any structural changes because when I was using this electric furnace, the fibers themselves are exposed to long temperature gradients for extended period of time. For example, if I put in a sample at 7:30 in the morning, I really cannot remove it from the furnace until late in the morning. So it's a long process in which these fibers are exposed to these high temperatures. And as you can see in this SEM images, there's degradation seen in the core of the fiber or throughout the fiber cores. Next slide. So I need a new approach. And at the time, I was also working on microwave sintering of ceramic materials using microwave. And in that case, a silicon carbide is used as a susceptor. A susceptor are materials that can absorb electromagnetic energy and convert that energy into heat. So that's when I had my aha moment of using the microwave furnace to try to strengthen the silicon carbide toes from commercial sources. In this case, it's we have a single mode microwave furnace. It operates at 2.45 gigahertz, and it has a power up to 2 kilowatts of power. And during operation, since this is a single mode microwave furnace, we are either centering in the electric field or the magnetic field, and this is accomplished by establishing a standing wave within the furnace. Next slide. So before we move on, let's take a look at some of the difference between electric furnace and microwave furnace, in particularly for this type of material and structure because they are thin fibers. In the electric field, you mainly have conduction and convection heating, slow heating rates, 4 degrees per minute, and the silicon carbide surface is exposed to long periods of temperature gradients as the temperature is ramping up to the heat treatment or whatever process you are doing on the fiber, and then the cooling process. And that leads to non-uniform microstructures. And typically it requires high power and high energy to accomplish this. In the case of the microwave furnace, microwaves couple with the susceptor, inducing electron excitation, resulting in heat generation. It has very fast heating rates up to 1,000 degrees per minute, has lower processing temperatures and power needs, and you can get a uniform microstructure because of the rapid heating and the rapid cooling, that you're not having excessive grain growth within your microstructure. And in this case, we can center in either the magnetic or electric field, as I mentioned before. Next slide. So one of the first things I did was just take a piece of fiber, of ceramic fiber, and heat treated it. And we looked at some SEM images, scanning electron microscopy, to see if there's any differences in the microstructure. And although this wasn't conclusive of healing or strengthening, it did show some promise. The resolution on the SEM is a little off, so wasn't sure. We needed to do more studies, but it was enough to get me started further on this project. Next slide. So before I get into what we did, we also have to consider that there's a lot of processing challenges with the microwave. However, once you've overcome a lot of these challenges, the process can become quite routine. But some of those challenges would be like calibration of the standing wave, tuning the microwave once you have your material inside the furnace, temperature limits, preparing the quartz tube, sintering area is small. In our particular research furnace, there is manufacturing furnaces where some of these things can be overcome. Another problem is sometimes the inert gases, if the power is added very fast or quickly, or depending on the material that's in there, you can generate plasma. Surface charge can also happen depending on constituents in the fiber, or in whatever it is you're sintering, or within just the cavity where your charge is building up within the cavity of the microwave, and you could have arcing events. Okay, next slide. So in our case, one of the process was really quite simple. Once we worked out all the hard details, and here you can see our furnace here in this upright picture here, where you see the coupled sample. That's where the sample is loaded. So typically we prepare the samples for loading in the microwave. We heat treat the samples. The furnace cools in about 30 or 60 minutes, sometimes sooner or later. However, it's about an average of an hour. Samples are then prepared for tinsel testing, then tested. So samples can be sintered and tested in one day, with time to spare for other exciting things in the research life of a scientist. Okay, next slide. So when we first started our more rigorous experiments, this is where we're working out a lot of the processing parameters, aligning the fibers using different gases. But one of the first things we did is we took some silicon carbide tow, and we cut that over an inch to an inch and a third sections, and then every other piece of tow was heat treated in the microwave. And we did that because the structure of the microwave, of the fibers, excuse me, and individual filaments within a tow is going to vary along the length of the material. And so we wanted to get a good representative of the microstructure changes to see if this was really working. And as you can see in our Weibull distribution, when we tested the as received ceramic fiber, we had a very low strength compared to the manufacturing strength reported, which is, I believe, 3.2 gigapascals, and we're getting 0.4 gigapascals, which was indicative of several failure modes. Now, this spool was an old spool. It's probably been there for more than 10, 20 years, who knows. So it was actually a good candidate to see how the microwave furnace worked. And what we see here is in a table we're looking at how long we left it in the furnace, the power that we used, whether it was coupled or not, and whether or not there was any arcing events. If it didn't couple and we didn't have any arcing events, those are the samples we considered. So only the ones that coupled. And what we saw was an increased strength of up to about 1.1 gigapascals, which is over 190% increase over the average strength of that we had obtained earlier of 0.4 gigapascals. Next slide. So this led to a lot of questions. So can we repeat the results? Can the strength of the silicon carbide toes be restored to vendor strength? The electric field was used in the heat treatment of the silicon carbide toes. Will the strength change in the magnetic field? The silicon carbide toes are manufactured with different compositions. So do the non-silicon carbide constituents affect the microwave processing parameters? Will the strength go up or down in a high strength toe? And what is the lowest temperature we can achieve? And what is the lowest power we can achieve? So let's take a look. Next slide, please. Oh, here we are. Sorry. Okay, so these are the three fibers that we looked at. They're from three different vendors. We looked at high nickel on S, ceramic, and Tyranno. If we look at the non-SiC elements, we have 0.7% oxygen in the high nickel on, and the ceramic 0.1 oxygen, 1.2 boron, 2.4% titanium. And then in the LOX-M, we have a high percentage of oxygen and 2% of titanium. And then the vendor strength or reported strength by the vendors is 2.8 for the high nickel on, 3.2 for the ceramic, and 3.3 for the LOX-M. The actual strengths that we measured in the samples that we had are high nickel on measured as reported by the company, whereas the other two measured at approximately 0.4 gigapascals. Next slide, please. So let's look at the results for the ceramic silicon carbide toes. What you'll see in this table is that we have a significant increase in the average tensile strength that we measured compared to the measurements that we had, not the vendor measurements. The temperature range from 1200 to 1600 degrees. Power ranges from 60 to 100 watts. Dwell times from 5 to 15 minutes. And longer dwell times at higher temperatures exceeding 1400 degrees C showed complete healing to full strength or higher. So when you look at this, you can see that we're starting to get, well, it was not to full strength. We think that we could get to full strength. That's what I meant to say, excuse me. And then when we look at the magnetic field, we had a much higher increase in average tensile strength. The temperature range is less than 800 degrees C. And the reason it's less than 800 degrees C, and I'm not giving you an actual temperature, is because the pyrometer that we were using in this system measures temperatures from 800 to 2000 degrees C. So we noticed that it was getting hot, and so we kept doing the test from 60 to 100 watts and from 5 to 15 minutes. And in one case, we were able to sustain an arc for 1 minute, and it showed some promise. But you can see that in the magnetic field, when you look at the table, there we are reaching temperature strengths that exceed the actual strength of the or getting close, actually 3.4 of the actual strength of the ceramic of the vendor strength. So we believe that we can reach these higher strengths. So the vendor strength or higher may be possible. The magnetic field, the electric field sintering is limited by the titanium boride that often forms in this type of material. And coupling power will determine the temperature, the dwell time, in both fields. Thank you. Next slide, please. So now the testing results for the high nickel on S. And in this case, the fiber, as you recall, had the same strength as the vendor reported fiber. So what we saw here was about a 15% increase in the vendor tensile strength. Temperature ranges from 1000 to 1200 degrees. Power ranges from 50 to 60 watts. Dwell times from 3 to 10 minutes. Longer dwell times with higher power decrease the strength. And now in the magnetic field, what we see is about a 12% increase in vendor strength, over vendor strength. Temperature ranges from 1000 degrees C to 1400 degrees C. Power ranges from 50 to 100 watts. Dwell times from 20 seconds to 30 minutes. In summary, the toe strength is strengthened in both fields. Coupling power will determine the temperature, determine dwell time in both fields. As temperature and power rises, dwell times decrease. And here we'll really see some nice numbers here for the average strength. And we see that at 1340 degrees C, 100 watts, 5 minutes here at the bottom of the table really produce some of the best results for strengthening the fiber toe. Next slide, please. In the case of LOXAM results, we didn't have a lot of fiber, and this fiber is really not produced anymore. But we're going to take a look at what we did see. We had a 173% increase over the average strength that we measured. The temperature range from 1000 to 1400 degrees. Power ranges from 50 to 80 watts, and dwell times between 10 and 20 minutes to see any effects. And in summary, we had relatively good results for the M field healing, and but more studies would be needed, and we could study other Tyranno toes that are similar. However, we have not done that yet, but we can consider those, and that's because the LOXAM is no longer available. But we do believe that we can get to much higher rates, and hopefully in the electric field, depending on how the material behaves, we could have some results in that as well. Okay, thank you. Next slide. Okay, so did we answer all the questions? Well, can we repeat the results? Yes, we were able to repeat the results. Can the strength of the silicon carbide toes be restored to manufactured strength? Yes. The electric field was used to heat treat the silicon carbide toes. Will the strength change in the magnetic field? Yes. SiC toes are manufactured with different compositions. Do the non-silicon carbide constituents affect the microwave processing parameter? Yes. So we saw sintering and healing parameters depend on the field, which one we use, either electric or magnetic, and non-silicon carbide constituents and coupling power. Will the strength go up or down in the high strength? It does both. What is the lowest temperature that we reached? Somewhere below 800 degrees. We really have to do some more studies to actually measure that temperature. And the lowest temperature that we had good results in the electric field was 1000 degrees, depending on the non-constituent components of and the coupling power of the fiber toe. And what was the useful power we used? It was approximately 60 watts. Next slide, please. So in summary, the microwave sintering can restore low-strength commercially available SiC toes to manufacturing strength. In my microwave sintering can increase the strength of commercially available SiC toes. Single-mode microwave sintering can heal damaged silicon carbide toes, and SiC toe strengths can be tailored to application needs. And some of the benefits of this process is fast. It's a fast process. It's a low energy, low cost process, and it has healing capabilities. Okay, thank you. Next slide. And I do want to acknowledge my colleagues, Dr. Amjad Al-Mansour, Janet Hurst, and Diana Santiago for their support in this project and other technical advice that they give me. And then during this process, we also had 3 students working on these projects, and I want to thank Felipe de la Torre from the University of Texas, Rio Grande Valley, Jonathan Lee from Yale University, Hannah Christiana Clark from Texas A&M University. Okay, next slide.
Thanks so much, Maricela. That was great. We received a number of questions during your presentation, and we'll get to them shortly. First, I'm excited to talk about NASA, Glenn Research Center, and accessing NASA's technology for commercialization. Technology transfer has been part of NASA's mission since its formation, where it has been encouraged to share the work of the space agency for the benefit of all. In the 1980s, Congress passed additional legislation that allowed other federal laboratories to transfer their technologies, and more recently, President Obama reiterated the value of federally developed technologies to spur innovation in the marketplace. Following this mandate, NASA Glenn Research Center has prioritized technology transfer by developing partnership opportunities that promote innovation, NASA technology commercialization, and small business growth within Ohio and surrounding states, and enhancing communication and collaboration with industry, academia, government, and other federal research laboratories throughout the Midwest region. NASA has 10 field centers located throughout the United States. In addition to the field centers, NASA has many installations where highly specialized testing, building of aircraft and spacecraft, and verification occur. NASA Glenn Research Center, Lewis Field, is located in Cleveland, Ohio, along with the Neil A. Armstrong Test Facility, formerly the Plumbrook Station, which is located nearby in Sandusky, Ohio. Each field center and installation provides unique services, research, and technology to further NASA's mission. NASA Glenn develops novel technologies in a number of key areas and is the center of excellence for power and propulsion, along with materials and coatings for extreme environments. Glenn Research Center patents roughly 10% of all invention disclosures submitted. Glenn has over 200 patents and patents pending available for license, but this is just the tip of the iceberg. The Technology Transfer Office has worked hard to make finding technologies easier by creating industrially relevant categories you see here. All patented and patent pending technologies from each field center are sorted into these categories. And they can be found very easily by searching our website, technology.nasa.gov. For the purposes of technology transfer, there are 3 types of partnering mechanisms that NASA uses: patent licensing, software usage agreements, and Space Act agreements. We'll talk about each of these. First, we'll take a quick look at NASA's patent portfolio, accessible at technology.nasa.gov. NASA's intellectual property has been grouped into 15 categories. Each of these categories is searchable by keyword, as is the entire portfolio. Licensing from NASA is easy. We offer 4 types of license agreements to meet your needs. The evaluation license agreement allows for a sort of test drive of a NASA technology. It has a set fee and a set term of 1 year that can be renewed annually for up to 3 years. The evaluation license allows a licensee to investigate the commercial viability of a NASA technology with minimal risk. The evaluation license is not a full rights license. NASA restricts the right to sell or offer for sale. The Startup NASA license agreement is ideally suited for startup companies. This license has set business terms favorable for startup companies. The terms are no upfront fee and no annual minimum for the first 3 years. There is a running royalty rate on net sales that start on day 1, and an annual minimum royalty begins in year 4. This is a non-exclusive full rights commercial license. The government use license is for entities seeking to use NASA technology in support of a U.S. government-funded project. These licenses have no fees or royalties, but do have a term matched to the period of performance for the U.S. government-funded project. This license is ideally suited for SBIR, STTR, contracts, grants, cooperative agreements, and in some cases, Space Act agreements. This is not a full rights license. The licensee may only use the technology in support of its U.S. government-funded project. Finally, the commercial license is a full rights license that is individually negotiated. These licenses can be non-exclusive or exclusive in a field of use. In addition to patents, NASA also develops a large array of software codes to support our mission work. NASA makes these software codes available to U.S. entities at no cost. As you can see, the software is organized into convenient and industrially relevant categories to make searching and browsing easier. NASA transfers executable software codes via software usage agreement. The software usage agreement contains terms and conditions specific to the release of that code. To search or browse available software, visit software.nasa.gov. NASA also partners with industry and academia using the Space Act Agreement. Space Act agreements are very similar to cooperative research and development agreements, or CRADAs. They outline the statement of work, specific tasks and milestones, who is paying for what, data and intellectual property rights, liabilities, etc. Space Act agreements come in two flavors: reimbursable, where the partner pays for NASA's cost to perform the work, and non-reimbursable, where NASA and the partner pay their own costs for performing the work. Generally, non-reimbursable Space Act agreements are used when the proposed work furthers NASA's missions, and reimbursable Space Act agreements are used when the proposed work is in line with NASA's missions, but does not help advance it. There are a number of other factors that go into making this decision, and Glenn's Space Act agreement managers are available to assist in making this decision. So I hope that you now have a better understanding of how to access NASA's technology. I also hope you come away with a feeling that NASA Glenn is ready and open for business. NASA Glenn's Technology Transfer Office is available to assist you. Please feel free to reach out to me or my colleagues with any questions. So now that that's done, we can move on to some questions. We've received many questions after Maricella's presentation, and thank you to everyone that has submitted so far. Feel free to continue submitting your questions by typing them in the chat box. If you have any questions for Maricela about this presentation, we will stick around to answer those questions as well. If we don't get to all of your submitted questions today, we will follow up with you by email afterwards. So, hang on here. I'm trying to get to the questions. Okay. Let me see if I can make this bigger. I'm sorry, Maricela, hang on here.
Can you read them to me?
Yes, yeah. I got it here. I found them. Okay. How do you determine the temperature of the sample?
We're using a pyrometer. Because we know that it's not absolute and there could be some variance, we do have a steady state temperature. So if we weren't able to get steady state temperature, then we would not record it and just say, you know, I actually did not even use that data in this presentation. So we did have times where the coupling is not working, but we're using a pyrometer. It's an Omega pyrometer. It came with the unit when I started working here, so it was already installed and on the instrument. But yeah, it's a laser infrared pyrometer.
Very good. Have you tried other types of fibers like high Nicolon type S? Does this technique provide the most benefit to non-stoichiometric silicon carbide fibers?
It may. I think there's got to be some consideration when you don't have a lot of other constituents in the material, and because it couples so well with the microwave that you could have runaway heating or thermal runaway on the fiber. So in this case, you have to be really careful with the power that you're using. We stepped it up very slowly, and as soon as we were able to tune it and couple it, we stopped at that power, and then we'd measure the actual temperature we're able to achieve in that particular moment. But I think it could have that strengthening power in other fibers, and it would be something that we would have to look at.
Did the density change in any of the materials?
We did not measure the density. However, we believe that we did. We did a lot of characterization on these, and they really just didn't show much difference as far as the microstructure goes. We did not do the density measurements during this time because we really had students working on it. We really actually didn't have that set up and ready to go. Most of our interest was in, the effects, the total effects. So yes, more studies need to be done on the density. But we believe that that was part of the healing process where we're possibly either removing carbon off the surface of some of the fibers or healing defects on the side of the fibers along the length, so that when they're in tension and they're pulling and rubbing against each other, it's not initiating a crack. We're still trying to understand exactly what it is that happened. Amjad is also my colleague on this. Amjad, do you have any comments on that question?
Hi, Maricela.
Hi, Amjad.
Yeah, I think you addressed that question very well. Between the two big things that we've done here, the various heat treatment methods, and then the strength measurements, and it really showed clearly the influence of this type of heat treatment on the strength of the various types of silicon carbide fibers.
Thank you, Amjad.
This one's a little bit long. Are you ready?
Mm-hmm.
Okay. Could you try heat treating boron nitride coated fibers in the microwave furnace? Since the fibers could get damaged from the high temperatures needed for the boron nitride deposition process, I wonder if you can get the same benefit without damaging or changing the structure of the boron nitride coating. Or is the idea to do this heat treatment prior to the boron nitride coating deposition? What are your thoughts?
My thoughts are, I'm not sure because I have to think about it for a little bit more. But I do think that you might be able to, because you're not reaching as high a temperatures as you normally need just for boron nitride sintering. So you could go to much lower temperatures. And we do know that the boron nitride will respond in a magnetic field. It's often used in physical vapor deposition. But the other thing is we did have one fiber that we tested in nitrogen with boron doping, and but we did increase some strength from the original 0.4 gigapascals that we had. I think we made it up to 0.9 gigapascals, but we didn't really examine that fiber and proceed with that fiber. We wanted to complete the first studies that we were doing first before we went on to that. But yes, I do believe it's possible. You might even be able to using a silicon carbide susceptor to convert your polymer into the silicon carbide in an environment, so that first you cross-link the fiber, of course, the polymer fiber, and then you could heat treat it. And we've shown that before. We have a publication in collaboration with the University of Texas, Rio Grande Valley, Dr. Karen Lozano, where we did convert the polymer into silicon carbide using microwave irradiation. And so it is possible then, I would suspect, that you could convert the fiber and then add a nitrogen atmosphere, or I guess you'd have to play around with it because you usually use ammonium for the gas in developing boron nitride, but you could possibly do it with nitrogen and doping boron.
Very good. Do you have any TEM image of a microstructure of the individual fiber to see the changes during the microwave sintering? What phenomena is happening during the microwave sintering?
We do have TEM imaging of the as received fiber, and then some of them that showed the high strength and some that didn't show that much strength improvement or weakened the fiber. And to be honest, we really just couldn't see any significant changes in the microstructure. I'm not sure if it was just that particular sample or if we need to just repeat those to see if we could see some changes. But as a matter of fact, the reason I didn't include them here is because we just didn't really see anything worth noting at the time, and we've had them analyzed, and pretty much we really couldn't see a difference between the as received and the heat treated fibers.
Very good. You mentioned that you are restoring the strength to the manufactured strength. What is the reason the strength was lower than the manufactured strength? Is it age, loading testing damage, or something else?
I don't think it was loading and testing damage, because this was the samples that the high nickelon and the ceramic samples came directly off of spool, so they hadn't been tested before. It could have been just aged or where they were kept, and they might have been damaged during some storing process and moved, and I really don't know. So these spools have been around much longer than I've been alive, I think, sometimes. That's a joke, but no, they've
Can I
been
add
around for a
something?
while. Yeah, go ahead.
Yeah, so usually there is a variation from between the strength that we measure in-house and what the manufacturer reports. Okay, and that may be due to several reasons. It could be dependent on the type of fibers, such as ceramic fibers, where the microstructure vary as a function of length within the spool, where you have areas that has more core and shell effect and not fully uniform microstructure. So that can be a reason for measuring low strength in-house much lower than what the manufacturer reports. So I just wanted
Right.
to mention
And,
that.
and I think typically you wouldn't see such a low strength. I mean, unless, if you're ordering a fiber that has a certain strength and you didn't get that, I imagine you could return it and get another one. So it could, and yes, and if you saw in my presentation also, I mentioned that particular spool showed several failure modes. So that could be almost anything. It could be defects, it could be inconsistencies in the microstructure along its length within each filament. And then you have some filaments, some toes that are 800 filaments, and then the other toe was 500 filaments. So there's variation in there, and there's always going to be variation between actual filament and the length of that filament and actual toe and the length in that foot. There's going to be a variance of strength. So that's why we looked at the average and the average standard deviation.
What percentage of final parts use fiber lengths of the nominal 1 inch used in the microwave healing testing?
Well, when they're loaded in a, if you saw those little cardboard things with a fiber, that's usually a 1 inch. So in the testing, the tabs of the cardboard frame hold the fibers. So the fibers are glued to the tab, and then another tab is put on top of it to secure it.
Mhm.
And testing is that, so it's about 1 inch that's actually exposed within that tab. I think that
Yeah.
answered the question. Okay.
Very good. Do you foresee treatment of continuous toe in a non-batch process or of an entire reel in a batch process?
Absolutely. Manufacturing, microwaves in manufacturing is already available. So I think we have actually an idea that we've submitted in. It has not gone through the full patent process, but we do have a disclosure on 2 processes for either this single filament and a component that you could actually, let's say, for example, if you had a small component that was in use, and instead of discarding it and replacing it, you now can just heal it, so that you could actually use this process to heal components and then reuse them in your applications. So yeah, we do. There is a way. It's rather simple.
So you can use this then to heal full CMCs, which include both the matrix and the interface material?
It could. Now we'd have to do some studies. We speculate that it could possibly do that, but it's also going to depend, right, on the component, what strengths you're trying to achieve. But if it's something that's lost a lot of its strength, we certainly show that you can restore a lot of the strength, at least to manufacturing strengths of the individual toes. So it's really just a matter of having the right microwave furnace, and depends on the size of the component, because the mass of the component is going to interact with the radiation of the microwave. So you'd have to make sure that the whole component is getting enough energy so that you achieve those strengths. But we have an idea for that as well. So just a little bit more work that we need to do, but certainly it can be done. And I think just even working with a manufacturing company in microwaves, I mean, this is stuff they already do.
So what effect do you expect in a fully crystalline silicon carbide fiber? Will the crystals grow, and will this induce reduced strength and creep resistance?
I'm not really sure. We think that they can grow, but they cool so fast that we don't think that there's really much changes. When we did some grain measurements, we really didn't see any different size changes in grain for, I believe it was the high nickel on S, that we had someone look at. However, through those TMs, it's very difficult to tell for sure. So we really need to get that done again and get better quality imaging so that we can really see the changes in the grain. But because we're heating it rapidly and cooling it rapidly, you're reducing the opportunity for excessive grain growth and getting uneven microstructures. Now, a CMC component may be different, but the same. You're not putting it in a furnace and then for example, in a batch furnace where it experiences or could experience a lot of grain growth while it's even just cooling down on the outer surfaces of the component, for example. Judd, any thoughts on that?
Yeah, Maricela. Yeah, one can expect enhancement in creep resistance if the crystals grow to an extent, you know. But you know, there might be a benefit here by the reduction of the second phases that this heat treatment process may do. Especially on the surface of the fibers, for example, Heineken S fibers, where when it's manufactured, it usually has 20 to 30 nanometers of carbon layer on the surface, and then surrounded by a PVA sizing layer. So both of those layers, they need to be removed prior to the implementation of those fibers in CMCs for the different applications. So the industry currently uses the just Bunsen burner flame to remove those layers. So this heat treatment, you know, has the potential of uniformly removing those layers, which will enhance the interfacial stability of those fibers when implemented within a CMC, because the strength properties, proportion limits, the mechanical behavior of CMCs is highly dependent on the stability of the interface between the fibers and the BN interface and the matrix. So if we can get rid of the carbon layer on the surface of the fiber, I think we have a good chance of improving the durability of those composites. That's all.
And you might be able to even, let's say, lower the temperature by lowering the power and sustaining it for a while if you wanted to induce grain growth. And what those temperatures look like, I don't know, because we haven't done that yet. But I imagine if you wanted to, you might be able to do that.
Very good. Why does prolonged exposure to microwave lower the mechanical properties? And do you have an idea on how many times the fibers can be sintered after damage? Is there a maximum number of times they can be repaired?
That I don't know. Now, I'll answer the first question, which was, what was again? I got lost in my thoughts. Sorry.
Why does prolonged exposure to the microwave lower the mechanical properties?
I think at that point, it may be either some amorphous, where the crystalline part of the material, it might be becoming amorphous. I'm not sure. There's different things in the microstructure that could be happening. The problem is we weren't able to see this. So I theorize that it's too much exposure, that the more power, what we saw is sometimes when you had higher powers like 140 watts or 400 watts, we really didn't see any benefit as far as strength, but we also didn't look at the microstructure. So what I'm thinking is that that there is no benefit, and it may be making the material more amorphous. And it could be that maybe some of the fibers that we initially sintered, where we did see an increased strength, maybe we were able to crystallize it, whereas the other ones had, for some whatever reason, were more amorphous. I'm not really sure, and that's more studies that we'd have to do. And it's a good question. I appreciate that. As for how many times can it be healed, we haven't tried that either. We just know that we took some really low strength fiber that should have been a high strength fiber, and it was able to, we were able to strengthen it. So I think it depends on the type of damage and exposure that it has. If, for example, it's becoming very, very oxidized, it may not work. Or if other constituent things seem to penetrate the CMC or the fiber or the toes, for example, that may be then harmful during the microwave process. But as far as these other, the one thing that we can say is that for fibers that were degraded or not very good quality, because even during manufacturing, not all the spools come out where you can use them. Sometimes they're unusable because they're unusable because you're not getting the actual strength that they're trying to achieve for a certain component. And in this case, you could actually take those spools and actually heal them so they can be used. But that's a very good question, and it's something to look into. Thank you.
Is there a theory of why the strength of the Tyranno and the ceramic are improved significantly by microwave heating, whereas the high nickel S shows only a minor increase in strength after microwave heating?
I can only think that it has something to do a little bit with the constituents. And what we saw was more in the magnetic field. Is that what the question was? Why we saw it more in?
Yeah, basically, why was there the strength of the Tyranno and the ceramic were improved more so than the high nickel through the microwave treatment?
Oh yeah, the high nickel already had a high strength.
Okay.
The Tyranno fiber had an average strength that we measured of about 0.4 gigapascals, and the ceramic also had an average strength of about 0.4 gigapascals. So those actually, if you look at the slides, and you'll be able to see them again soon, but where we show the distribution, the Weibull distribution, those are just showing us that there's failure modes in that particular, and that the reliability of that particular tow would be very low. So I think part of the heating process is that there's going to be a limit, and it depends on the constituents. So in the ceramic and also in the Tirano, they both have, I think, titanium in them, and it could be that that's reacting and helping in aiding in sintering, or the boron, because they have those sintering aids. So in the case of this of the high nickel on S, where it's much stronger already to begin with, so we didn't see that high jump, right? So we saw 14% and 12%, but we did get some strengthening if that's what was needed to be achieved for that particular fiber. So their manufactured reported strength is approximately 2.8 gigapascals. That's what we measured when we tested it. And then when we did the strengthening, we also saw that it lowered at the higher temperatures and the longer temperatures. So we're not really sure of all the mechanisms going on. It's something we need to investigate further. But thank you. Very good question.
Do you think plasma generated in the microwave under inert conditions could be harmful to the fibers?
I think it could be, but I don't know. So we'd have to really have a controlled study before we can make those determinations, because it also may be helpful if you're trying to use a coating, for example, in the fiber. So we did see plasma quite a bit in the initial studies and arcing events, and we did have some studies where we actually maintained the arc. Try to, and what I'm saying there, it's not like a steady arc like you might see in plasma or spark plasma sintering, but we did see an arc that was to somewhat controlled up to 5 minutes, and we did see some strengths. But until I really get a chance to look at those and understand them, I didn't really want to report on that. But for 1 minute, it looked pretty good, but then when you got up to 5 minutes, it decreased. So arcing could also be a problem. I imagine that the plasma, it just depends on the fiber, if it already has a coating, if it doesn't have a coating, if you're trying to put a coating. And we haven't done those studies, so I really can't comment on that as to whether or not it'll be damaging. I think it could be helpful.
For the tensile testing, did you measure tensile strength of tows or filaments?
We did a tensile testing of tows.
And do you have a plan to test newer procured fibers to see if if there's a strength increase like that of the older fibers?
We could. We don't have any plans right now. This project was funded through another project, and it was really just kind of a side thing that we're doing with students who did a fantastic job. But yes, if we were to get some funding, we could proceed with more studies and really understand what's going on and what else we can do with this technology to increase the strength. Because one of the things that I noticed is when you see silicon carbide in microwave sintering, a lot of times they use it for nanoparticles, but I see a lot of people using high power, and I've never understood why, because we always coupled at low powers. We hardly ever used the power. I think we did it one time where we went high power, that it was beyond 400 watts, where I got into the kilowatt power range, but then I started having thermal runaway, and just shut it off.
And finally, can you share the brand of the microwave furnace that you used for your research work? Do you happen to know that offhand?
I do not. I do not know.
That's okay. We can respond later.
Well, what I can say is that you can have them built. This one was built about 4 or 5 years before I even joined NASA Glenn through a contract. And I did try to contact that company at some point. When I first arrived, it was actually not working. And so I tried to contact the company, and they were no longer in place. And so I contacted another company that makes microwave furnaces, and I was able to get them down here, and we fixed some parts, and we did some training, and we got it running. So really, there's some microwave experts out there, and I'm pretty sure you could build one or buy one for a relatively inexpensive price. I
Very
think.
good.
I don't know. They may be more expensive. I have no idea, actually. I don't know why I said that, but I just know what this one was paid for many years ago. But who knows? Whatever. Sorry. Sorry.
That's okay. Thanks, Maricela. So that's all the time we have for our questions today. If we didn't get to your question during the Q&A session, then we will follow up with you by email within the next week. If you have additional questions, then please feel free to submit them to the email address at the very bottom of the screen, and we'll be sure to follow up with answers to those as well. Once again, we really appreciate you taking the time to be with us today, and we will be in touch. Thank you, everyone. Have a great day. Take care.